So now substitute the expression for Qn of y. We have got this minus C ox V of VGS minus V of y minus Vt into mu n into E. And we know that the electric field is a gradient. Electric field, it is rate of change of voltage. So I can write this electric field E as dV by dy. Electric field is rate of change of voltage. When there is an electric potential gradient, you have electric field. So in this expression, I'm replacing E by dV by dy. Now cross multiply id into dy equal to this expression into dV. If you want to find id, integrate both sides with respect to dy. I'm integrating with dy, and dy is the length of your channel. So channel length varies from 0 to L. So see, I'm integrating from 0 to L, and this side is voltage. Across channel, I'm applying voltage VDS, so I am integrating from 0 to VDS on this side. So this side is just id into L equal to, if you integrate, you will get the answer VGS minus VT minus VDS square by 2. So if you integrate, you get this answer. So this is the expression for drain current in the triode region. You can see the relationship is nearly linear. Linear in the sense you can see ID is proportional to VDS. When the VDS is very, very small, VDS square will be even more small. So I can neglect this term. I can write ID proportional to VDS. So it is output is proportional to input. So I can call this as the linear region, or it is called as a triode region. In a triode region, MOSFET works as a voltage control. It is just a resistance. I told you it is just a variable resistance, and the variable voltage comes from VDS. So as long as VDS is small and controllable, this MOSFET works as a resistance in the triode region. This is the expression for drain current in the triode region. So once this VDS becomes large, more than VD sat, then we have what is called as the pen